Hi, this is Roland from Brain MRI. In this video we will explain a new method to automatically segment the thalamus in MRI brain images. As you might know, the thalamus is part of the forebrain and can be considered as the relay station of the brain. All information from your body's senses are processed by the thalamus and then sent to your brain's cortex for interpretation. Therefore, the thalamus plays an important role in consciousness, learning and memory. And in patients with MS, with multiple sclerosis, the thalamus is often affected already in a very early phase of the disease. This is the reason why MRI-based thalamus volumes can be used as a predictor for cognitive impairment as well as for therapy monitoring. Now, as explained, measuring the thalamus volume on an MRI is important for patients with MS. However, to measure the thalamus manually slice by slice is not feasible in clinical routine. And existing pipelines for automatic thalamus segmentations are sensitive to the MRI scanner platform, and therefore results from different scanners cannot be directly compared. Now, our goal was to develop an automatic thalamus segmentation which is fast, accurate and robust. The approach was to use a 3D convolutional neural network, so a 3D CNN, and to train that network on a large heterogeneous dataset covering the whole range of image characteristics, as indicated here on that slide. So for training we used MRI images of nearly 2,000 patients which were acquired on 170 different MRI scanners. As a second step, we had to generate thalamus ground truth segmentations for the training. Since it was clearly not feasible to segment the thalamus in all images manually, the ground truth segmentations for the training were generated automatically by the FSL software. You might ask yourself, if FSL provides already automatic thalamus segmentations, why do we need to develop a new algorithm? The answer is that FSL has a number of disadvantages. First of all, it's quite slow, it has a relatively high failure rate, and it's quite dependent on the scanner hardware. So the new 3D CNN algorithm trained on FSL segmentations should overcome these disadvantages. Now, to even more increase the heterogeneity of the data during training, we applied massive data augmentation by adding, for instance, artificial bias fields or noise to the input images. So the idea was to force the 3D CNN to focus on the relevant features rather than to tune the results too strongly to a specific image characteristic of a given scanner. As architecture, we used the classical UNet-like architecture with large 3D patches as input. We used 3D patches of 160 pixels in each image direction, so one patch approximately covered 2/3 of one image. We also tried the same approach with smaller patches, like 40 pixels in each image dimension. However, the performance with small patches was much worse. So one of the key success factors with that architecture here was really to use large patches. We validated the trained 3D CNN on several independent datasets. The first goal was to test the accuracy of the trained CNN. That means the aim was to find out how close are the automatic thalamus segmentations to segmentations created by human experts. For that we used a publicly available dataset of 18 MRI images, and for each of the images in that dataset a manual expert segmentation was available. And then we compared the thalamus segmentations from the experts to 3 automatic pipelines. In addition to our pipeline, the 3D CNN pipeline, we tested FastSurfer, which is a pipeline also based on CNNs, and the classical FSL pipeline. As explained, FSL pipeline was used to generate the ground truth for the training. Now the similarity between the three automatic segmentations and the manual ground truth segmentations by the experts was measured by the dice similarity coefficient and the Hausdorff distance. The dice basically describe the volumetric overlap between two structures. As you can see, the dice was quite high for all three methods. FSL was slightly better than the two CNN-based methods, however the difference was not significant. The Hausdorff distance measures the maximal distance between two surfaces. Also for this method, results are similar between the three methods. The 3D CNN and the FSL are slightly better in that case than FastSurfer. Overall, all three methods have an excellent agreement with the manual expert segmentations. As a second step, we measured the stability of the method with respect to changes of scanner hardware, the inter-scanner variability. To measure the inter-scanner variability, we introduced a new dataset which is called the Frequently Traveling Human Phantom dataset. If you want to know more about that dataset, there is a separate video which you find on our channel. In short, the dataset contains 557 images of the brain of a single healthy male volunteer, which was acquired on 116 different MRI scanners. The data can be downloaded for free. The link can be found under this video. We will use the frequently traveling human phantom dataset to study the inter-scanner variability of the three thalamus segmentation algorithms. The question is, how much does the thalamus volume depend on the scanner? Since it is the same subject, the thalamus volume should be approximately the same for all scans. You will relate the interscanner variability to the intersubject variability. Interscanner variability describes how much a brain volume or thalamus volume depends on the scanner, whereas the intersubject variability provides information to which extent the thalamus volume differs from individual to individual. Therefore, we analyze a second dataset which comprises MRI images of nearly 5,000 healthy individuals. And that data was acquired on 160 different scanners. Since the data contains data from different scanners and from different subjects, we can expect that that data reflect the interscanner and the intersubject variability. To estimate the intersubject variability, we first have to remove the influence of the nuisance variables age and head size. Head size was measured by the total intracranial volume, TAV. The brain volume is modeled with the bivariate quadratic function with age and TAV as variable. And we compute a least square fit through that data and we obtain that surface. A point on that surface tells us the average expected thalamus volume for a given specific TAV and age. Now, to remove the influence of the TAV and age, we compute the distances for all points to that surface. The resulting distribution reflects the interscanner and the intersubject variability. Let's now plot the FTHP data within that normal database. We also compute the distances to the same surface and to get a second distribution. The size of the second brownish distribution represents the interscanner variability, since it is the thalamus of the same healthy person. Now we compare the interscanner variability between the three methods. Here you see the plots of the same data but for the three methods. And as you can see, the interscanner variability of FastSurfer and FSL is almost twice as high as for the 3D CNN. That means the 3D CNN is significantly more robust with respect to the MRI scanner than the other two methods. And this is a huge advantage to apply this method in clinical routine. So in summary, the thalamus is an important marker for patients with MS. The proposed 3D CNN provides thalamus segmentations in less than 1 minute, which is accurate and robust. The frequently traveling human phantom dataset can be downloaded for free. If you want to know details about the proposed method, please follow the link under this video. If you found the content of this video useful, please press the like button or subscribe this channel. This will help others with similar interest to find this video. Thank you for watching this video.